AlphaGo never stopped improving. Like you could have, it became super intelligent and you could have sunk 10x or 100x more recent resources in it and get an even more super intelligent AlphaGo. And so in principle, these systems never stop learning. It's just a matter of how many resources you want to sink into them. Now with language models in RL, it's still early days. So I don't think that we've discovered the sort of maximally scalable blueprint. But there's a foothold.
Welcome to Manifold. My guest today is Misha Laskin. Misha has a background in theoretical physics. He has since transitioned to AI research and to founding his own AI companies. And so I think this interview will be especially interesting for people with a physics or academic science background, but also interesting for people who want to understand the current state of AI. So Misha, welcome to the podcast.
Thanks for having me, Stephen.
So I understand that you were an undergrad at Yale in physics and that you actually you finished a PhD at the University of Chicago. And maybe just tell us what the 20-something, early 20s Misha thought he was going to do with his life, why you were attracted to physics. Just give us a slice of life for you at that stage.
Yeah, I think that when I moved to the States, I'm Russian Israeli. And when I moved to the States, I got really interested as a teenager in two things. And it was physics and literature, basically. Literature is basically because I didn't read very well. And so I kind of, it was sort of like eating your vegetables until you like them. And so at first it was very painful, but then I actually started liking it. And physics, we had this, group of like the Feynman lectures in my parents' library. And I had a lot of time on my hands and there was just something aesthetically, I would say, really beautiful about it, of understanding pretty interesting implications that are non-obvious about how the world works from some set of first principles, ability to explain things very clearly. I just really enjoyed reading it. And so that's kind of, my initial inclination into physics began there in high school. And then I basically wanted to do things like that. I wanted to work on impactful science. I think that was the thing, work on impactful science. And I thought that physics would be the place for me. And so I got very interested in theoretical physics, did my undergrad in physics and double major in literature, but then professionally really wanted to go into the scientific realm, and did my PhD at U Chicago in theoretical many-body quantum physics. And I think, so it was actually a really wonderful time. I think it's I look back really fondly. It had this sort of, almost physics how I imagined it 100 years ago, because theoretical physics you can do, at least then, I don't know what it's like now, but then you could still do a lot of it on chalkboard. And so it was a lot of sessions with my advisor or some colleagues where we're deriving something interesting on the chalkboard. Yeah, it was a really fun time in my life.
And I think right after you finished your PhD, did you go into Y Combinator and start an AI company? Do I have the details correct?
Yeah. So towards the end of my PhD, I kind of sort of had I would say, a change of heart, not because I think that the stuff that I was learning was very interesting, but I felt that I became an expert in this very narrow sliver of science. And while it was aesthetically pretty beautiful and very interesting, it was hard for me to imagine the kind of impact that I would have, even if successful, right, in decades from now. I think that, yes, some people go into physics and I think that are able to see kind of maybe, I don't know, at a young age or older, depending on how patient they are, a great amount of impact. There were scientists like that around me, but maybe I was just impatient. It was hard for me to imagine waiting decades to know whether the things I was working on would bear fruit or not. And so I did this kind of I would say I think that my personal confidence went down then because it was sort of a bet that I took. I had a lot of conviction in it and put in almost a decade of my life into it, and then didn't really know, you know, what it is that I should do. But I wanted to try kind of doing sort of almost the most practical thing I could imagine. Somehow entering the job force or the workforce didn't seem that appealing. And frankly, I think to a physicist who's like just trained very theoretically, some of that is also a bit intimidating. You're kind of, you know, I I hadn't studied, CS, formally. And so it was all very foreign to me. So I taught myself to code. This was happening, I guess, towards the end of my physics PhD anyways, where I had to pick up coding for some of the projects I was working on. And I decided to do almost what I'd call a random walk through startup ideas without having like any, I would say, internal conviction at the time around what it is that I should build. I was kind of just random walk through, is this useful or not to, to someone else? And ended up converging on a company that was effectively building inventory prediction systems for retailers. So, how many items of clothing or, should you make for your next season or something like this? And I learned a lot about startups at that point in time, mostly about, I learned a lot about what I didn't want to do maybe during that process. But it was also interesting building useful stuff. It's just that there are some, I think, fundamental principles around startups that maybe I should have read some of the Paul Graham essays before, but I was reading them as I was building the startup. And I definitely think some of them are true, right? One of them is a simple notion of having deep empathy for your customer and sort of loving your customer. And the reality of it is that I didn't have very deep empathy for, for the people who I was trying to help, right, on the retail side. I didn't understand them that well. And so it kind of converged on this consulting business that was generating revenue, but didn't really have a product around it. And I wasn't, particularly fulfilled working on it either. But at the same time, I saw deep learning taking off. And in particular, I remember seeing AlphaGo. And that kind of changed something in me in terms of, I kind of think of that part of my life as wandering through the desert kind of part and trying to kind of put the pieces back together and find like what is deeply internally motivating to me. And when I saw that come out, that to me seemed like this is the impactful science of, the time that I live in that I really want to work in. And so I basically dropped everything I was doing and went into a cave where I learned deep learning and reinforcement learning fundamentals. And that was kind of my first foray into AI.
And what made you, so at that stage, you might have jumped immediately maybe to a company and start working on AI, but you actually went to Berkeley for an academic postdoc. So what was the thought process there?
I think at that time, AI as a useful piece of technology it was still not obvious that was the case. It was still very much, this was a number of years before language models took off. And it was still, I would say, there's both a lot of industry research happening, but it was more academic in nature, I would say. And I was considering two things. I was in the process at OpenAI. They had this fellows program for people who are coming out from a different field to sort of ramp up into AI. And at the same time, got introduced to Peter Beal, who is an AI researcher and professor at Berkeley, who's done a lot of foundational work over the last decade. And my decision at that point in time was, where do I think I'll learn most in the shortest period of time? And I thought that as a postdoc, I'd basically be able to iterate through a lot of different ideas and have a lot more learning events, which in retrospect, I don't think that that's necessarily, I think both options were great. But at the time, it was just not clear that AI as an industry, like as a commercial industry, was the place that would have the most impact. And it kind of seemed like the place where I would learn most at the time was still in the academic setting.
Now, at this point in time, were transformers a big deal already or just starting to be?
they were the, some of the foundational transformers papers had come out, but I remember this was right before GPT-2. So it was not obvious, when I joined the lab, again, so inspired by AlphaGo, I really wanted to do reinforcement learning, decision making, kind of solving the problem of autonomy. And there we were just using RNNs and LSTMs for anything that required memory, and oftentimes just MLPs or convents. So it was very rare to use a transformer in reinforcement learning at all. And they were taking off in NLP, but at that time, NLP was not, language understanding was one of the several like sub areas of AI. It wasn't, there was computer vision, there was, language models, there was reinforcement learning. And I would say that the thing that was probably most top of mind at the time was reinforcement learning, because it was just coming from, the AlphaGo breakthroughs. And it wasn't, when AlphaGo happened, it wasn't just AlphaGo, it was a series of papers of increasing, I would say, both they got progressively more beautiful in their simplicity and how many assumptions they removed, and kind of power. And so these were AlphaGo 0, which then learned the game of Go without any human demonstrations. Then Alpha 0, which generalized beyond the game of Go to other games. And finally Mu 0, which was an algorithm that sort of learned the rules of the game as well, instead of being given them. And so that was like the thing that was top of mind to, I think, the AI community at large. I think reinforcement learning was very top of mind. And even though transformers were definitely taking off in NLP, it was kind of one of the few things that was happening. It was not clear that that would be the big thing.
Do you feel, this is jumping ahead a little bit, do you feel a little bit like the field has come full circle now, where maybe RL is like, because of the recent reasoning models, like, or the ability of RL to condition these reasoning models, it's sort of now back at center stage a little bit?
I think it's getting there. It's been a pretty interesting turnaround, because after, I would say, GPT-3 and certainly after ChatGPT, I think the whole field of reinforcement learning took a bit of a backseat, and I wouldn't say it became irrelevant, since the workhorse algorithm that powers alignment of these models is RLHF. But it was really, RLHF is a pretty weak form of reinforcement learning. And a lot of people questioned to what extent it was even necessary, as opposed to just really high quality curation of instruction tuning data. So RL definitely took, I'd say, a backseat. And so after I worked on Gemini, which was Google's large language model, I kind of realized that I thought that the ingredients might be on the table, where you have these really general objects that are language models. And there's nothing fundamentally wrong with reinforcement learning. It's not like there's something that we learned that was wrong. It's just that you need a good reward signal to optimize against. That's basically the thing. You need a task distribution to learn from, and you need a good reward, like way to verify that those things are being solved. And so I kind of thought that, after we launched Gemini 1.5, that it was probably the time to start looking into scaling up reinforcement learning on top of language models. I think that's now come full circle in terms of reasoning models, which is also rather, I think, like one of those non-obvious things. I think a year ago, maybe, let's say a year and a half ago, reasoning models were one of the many things that an AI lab pursues. It was not clear that they would be as powerful as they're starting to get today. So I think we're kind of seeing is sort of, this is kind of maybe a normal part of these AI waves, is that the work starts, obviously kind of earlier, before it's clear to other people, but when it's happening, it's actually not clear that this is going to be the thing that wins, except for, for a small subset of people who have a long conviction and are seeing something that other people aren't.
Right. So coming back to your bio, because I skipped ahead, and so the audience doesn't really know what happened to you. So you did your postdoc for a couple of years at Berkeley, and then you transitioned to Google DeepMind, if I'm not mistaken, and that's where you worked on Gemini.
That's right. I joined DeepMind to continue basically scaling up research in reinforcement learning. And again, it was not clear to me that it was not really to work one language models at the time. It was uh, I joined a team that was called the General Agents team. So, it was really to solve the problem of agency and autonomy with reinforcement learning. This is a team led by Vlad Lee, who was the first author of DeepQ Networks and the paper that started basically the deep reinforcement learning era in 2013, I think. But then what happened is that I actually remember this very vividly. I was at NeurIPS in New Orleans, and ChatGPT came out. And that afternoon, I was giving a talk, and I had some kind of dissociative moment of, why am I saying these words? Like, the thing that matters is clearly, it's, I don't know, somehow clicked with me that it's so obvious, like what the thing that matters is now. And so why am I at the conference, talking about something that is not this thing? So as soon as I got back from NeurIPS, I basically dropped everything I was doing, started working on language models, and entered a project with, at the time, there's a small group of people that became the reinforcement learning and RLHF team for Gemini.
So just to clarify for the audience, so you're giving your talk at NeurIPS on, some research you've really poured your heart and soul into. But in the back of your mind, are you thinking scaling transformers as language models is the thing that really I should be focused on? And is that explicitly what you were thinking, or?
It was something similar. I was thinking the following. So the problem with reinforcement learning before language models was that we had developed these extremely powerful algorithms that worked in very narrow domains. So you had a super intelligent Go player that was hard to, if you want, it didn't really generalize to anything. You had to, if it did generalize, you had to, it did so in the sense that you had to retrain the entire model for a different domain. And the problem is that most domains of interest, it's just impractical to collect the amount of data and have, the verification signal that you need in order to get something useful working there. And so there was this big, like existential, I would say, generalization problem of we have really powerful systems. We have no idea how to make them general. And when ChatGPT came out, and I played with it that day, and it was very clear the system is very general. It might not be very capable yet. It's not autonomous. It's at that time, it was a pretty weak chatbot, but it was very general. You can ask it about almost anything, and still can, right? And it'll answer it. And sometimes very capably. I remember at the time we shipped a feature that formatted basically code as almost like blog posts about code. So you can ask it something about code and then it writes you a blog post. That was pretty magical. So what I realized is that we were, or at least I was, let's say, spinning my wheels trying to solve the generality problem when it had already been, like, it was solved for us already, right? That these language models are very general. And so it was just a different way to approach like the problem. And that's what I thought was really interesting.
When I was very young, before I actually learned any physics, I read books like Gödel, Escher, Bach. And so I was actually quite interested in AI before I knew any physics. And I always wondered about this problem of how would you instantiate knowledge about the broad world in your AI? And at the time, there was some very huge project at MIT, I think, where they were just literally typing true sentences into a database in the hopes that eventually it would reach some critical threshold and know about the world. And so the big thing they accomplished, which surprised me, was like, okay, transformer trained by next token prediction on trillions of tokens. Wow, you get a world model that actually knows a lot about the human world, as observed by human writing. And yeah, that was a 0 to 1 moment that was just shocking. And I think people are still probably underappreciating that 0 to 1 moment. Like historians will look back and go, yeah, that was a discontinuity in this whole thing.
Yeah, it's very non-obvious. Still, I mean, I think it's still non-obvious to me why it works. It's magical that it does, but yeah, because the internet is such a big, messy data set. And so when you pre-train a model on them, I mean, most of us don't actually get to, most consumers certainly never play around with like the actual pre-trained model because it's very user unfriendly. But I remember getting, access to some pre-trained checkpoints and playing around with them. And if you kind of poke at them the right way, you get to elicit some very interesting answers. And the fact that they have these powerful world models that are then, I would say, very steerable, like doing instruction tuning and reinforcement learning, you don't need to do it for that many steps before you go from your pre-trained checkpoint to something that is usable to people. And that was really interesting as well. So it solved, there was this whole field in AI before then, and maybe, still is now, but I think that this kind of was an answer to that of meta learning, which is the notion of how do I learn very quickly from a very small number of examples? And there are all sorts of sophisticated algorithms for how to do this. And it turned out that the best meta learning algorithms was just next token prediction on the internet. And from a meta learning perspective, few shot prompting is basically learning very quickly from a small number of examples. And that was really surprising.
Yeah, I think there's just some magic, in the idea that a big neural net, which is general enough, and you force it to do next token or get good at next token prediction, it builds structures within itself through that automated process that reflect, things about the world. And I think a priori, I had no idea that was going to happen, but somehow they stumbled on the right way or a way to do it.
Definitely. I think that it is really magical and something that was in the back of my mind. And I think there is a bit in which it's magical, but the magic fades in some sense, in that I thought there's only so much information you can extract from the internet. There's only so much that you can compress from it because it's sort of a fixed body of knowledge that's very noisy. And at some point, I thought we'd hit a point where you're getting diminishing returns from how much you can imagine, infinitely large brain that's soaking up everything on the internet. That's sort of the max of how well you can do. And it was just not clear at what point will we get there? At what point will we basically get brains on, say, the neural brains, these neural networks that have sufficient capacity where you've kind of extracted almost everything there is to extract from the internet.
Yeah, it's interesting because you don't want to go to the overfitting limit where you've literally memorized the 15 trillion tokens or something. You want some intermediate where it memorized some stuff, compressed versions of some stuff, but it built some structures also that reflect relations between the information that it's seen. So it just seems very non-trivial to me. Like I think one of the things I think people with a more like kind of theoretical physics bent in the future, when they have lots of these models to experiment with, will probably understand that dynamics better than we understand it now.
Definitely. I think another thing that was surprising about this whole pre-training era is that typically in machine learning, you have this notion of epochs, like you train over your data set multiple times, and you see where your training and test or validation curves diverge. And that's when you know that you're overfitting. But with pre-training, you do less than one epoch, basically.
Right.
You scan less than the total amount of data on the internet. So there is overfitting that happens because sometimes data is duplicated, right? Sometimes it appears twice on the internet, like an article might be syndicated or something like this, or things might be quite similar, but generally it's sort of less than an epoch.
Do you have a sense of whether we've hit, so in the scaling relationships that were in various papers like the chinchilla paper, it looks like if you want to increase model size by an order of magnitude or the amount of useful compute by an order of magnitude, you need substantially more, maybe the square root, more data. And at least according to those relationships, it looked to me like mid last year that we would run out of data before we ran out of compute or potential model parameter size. Is that correct? Like, is that what people within, say, Google would say?
I think that's roughly correct, that it's been harder probably to extract significant gains from the pre-training corpus than some people would have predicted. I think that there was a sort of sense of this can, just keep scaling, your model size, and you'll just get progressively better and better models, trained to the same pre-training corpus. Mm-hmm. And I think that we had already started seeing diminishing returns. And by we, I mean as a field. So, across multiple of these labs. And there was a moment where, at first, I think that there's clearly a lot of practical value to be derived from these models. And there's a lot of stuff that could still be done, even if you exhaust the pre-training corpus around instruction tuning, RLHF, and overall data curation and just optimizing the architecture. So probably, even if nothing else had changed, there would probably still be quite a bit of progress. But I think there was this fear of maybe this is as far as this idea goes. Like, right, you can make it more efficient, but how do you get substantially more intelligent systems? I think the North Star is still systems that help you do things autonomously, help you do the work that you want to do autonomously. So as a scientist, it might be, there's a bunch of the rote work of coding work and setting up experiments, these kinds of things that you might want systems with. But aspirationally, you want them to also help you discover net new knowledge and be sort of a patient collaborator. And it was less clear how just doing pre-training with some alignment with gas there.
Right. So were you surprised by, I guess maybe you were still at Google when the reasoning work started there, or were you involved in that at all?
So I was at Google when it started. I wasn't personally involved in the reasoning effort that was there, but I had some colleagues who were. And of course, I was working on the infrastructure and methods for RLHF and reward model training. And of course, that's the thing that makes these reasoning models work is the fact that it's basically learning to reason as a reinforcement learning problem. So there's definitely collaboration going on there, but I wasn't on the team that was working on reasoning.
Right. So the way I explain the reasoning, the advances in reasoning in the last, say, 6 months or something is, you get the model to, instead of giving you a quick answer, it sort of talks to itself and it learns the behavior of reasoning, and it can do more if it behaves in the reasoning way rather than in the sort of just immediate response mode. But my mental model of this, which I'd love to hear your thoughts on, is that, the pre-trained model is not getting stronger, but you're getting it to behave in a different way. It's more powerful or more useful in that new mode of behavior, but you haven't really improved the underlying model particularly. Do you think that's fair?
I think it's fair if you're talking about generality, in that I think the pre-training paradigm is the diversity of data on the internet is just very hard to recreate synthetically. Mm-hmm. But I think you are improving the capability of the model in its ability to think depth-wise. So for the distribution of data that you're training it on, be it math or coding or other verifiable data, it does kind of achieve a new capability. And I think about it very similar to how, if we forget about language models and look at how large-scale reinforcement learning systems were trained, they typically had a imitation learning component where you learned from some human data, and then a reinforcement learning component where you left off from where the human data ends and had the model self-improve until it became super intelligent. And that was the blueprint for AlphaGo, AlphaStar, OpenAI's Dota project, imitation learning followed by reinforcement learning. And I think the same thing is playing out now, where you can think about pre-training and instruction tuning as imitation learning on, right? All this data was generated by humans. Some of it now is also generated by AIs with synthetic data, but it's primarily human generated data. And that gives you a starting point where the model has non-trivial reasoning behavior out of the box. Like it's not that it had no reasoning behavior and now it does. It had non-trivial reasoning behavior, which is this whole line of work around chain of thought prompting that preceded reasoning. And then when you put this into an online reinforcement learning loop with a way of verifying the output that is reliable, that you can trust, like your verification. That is to say, if you can't trust your verification, then it can get hacked and your model won't reason in the right way. But assuming you figure out how to solve this type of reward hacking problem, then you're sort of reinforcing the good reasoning behavior that's already in the model. But at some point, you actually go beyond the distribution of what the model previously knew, and it's just learning net new things. And I think that's what's happened with these reasoning models, is that they've learned net new things that the pre-trained model did not know.
And the net new things are actually learned in the RL phase. So if I give it some kind of math problems and it's sort of adjusting its parameters in such a way that it can succeed on these math problems, that reinforces maybe its command of change of variables or some trig identity. Is that a fair way to think about it?
Yeah, I think a fair way to think about it is exactly what you said. And I think again, kind of the AlphaGo analogy holds here, where that system, AlphaGo and Zero, learned net new things, just net new strategies that were not yet in the corpus of things that humans knew. This famous Loop 37 from AlphaGo. And I think something similar is happening here, but maybe less, it's less drastic yet. I don't think we've seen anything close to Move 37 for language models of this obvious creation of net new knowledge. But it is, I guess one way to think about reinforcement learning is that it's a way of, you're generating synthetic data, and by having a way of verifying which traces in synthetic data are good or bad, you're kind of amplifying the good ones and downweighing the bad ones. And so once your agent accidentally stumbles on a strategy that worked, that thing gets reinforced and internalized. And that's where sort of this net new knowledge comes. At first it's an accident, but then it gets internalized into an actual strategy. I think that's loosely how I think about these things. And we're at an interesting phase now, I think, where reinforcement learning is starting to work again on top of language models. And but we're not yet at the AlphaGo moment for language models yet. There has not been this powerful net new knowledge creation yet.
So in the DeepSeek R1 paper, they're very open about what they did. So I like reading their paper, because with Google, with Gemini or OpenAI, I have to always guess like what they're doing. But at least with DeepSeek, they're just pretty explicit. So in that paper, there's the vertical axis is performance on some AIME math problems, and I think right-hand side is maybe RL steps or something. And it looks like the curve is bending over. So it doesn't, or at least the rate of increase with training, first is more dramatic, and then it's smaller. And in fact, at the end, as you could guess that it's sort of just fluctuating a little bit. It's not, if it is increasing, it's increasing very slowly. And so one interpretation of that graph might be, okay, without improving the base model in some other way that they haven't tried yet, even more continued RL along that direction wouldn't necessarily qualitatively improve the math ability of this model. Do you think that's plausible, or do you think maybe that's the wrong interpretation of that graph?
Well, I think, first of all, the thing that's pretty universal about when you look at reinforcement learning curves with language models or before them as well, is that they tend to be log linear. And so they, if they ran the experiment for 10x longer, I think, well, we may or may not see something different, but let's put it this way. If the verification was good, if the way of detecting that this thing was solved correctly or not was good, and the exploration of the model was decent, that is, it was trying reasonable strategies, then you would get this log linear behavior where it basically never stops learning. Now, it is reinforcement learning algorithms in practice do stop learning at some point, but it usually yeah, there are usually ways to overcome it. And so when you, I think maybe to give an example, going back to something like AlphaGo, is that AlphaGo never stopped improving. Like you could have, it became super intelligent, and you could have sunk 10x or 100x more recent resources in it and get an even more super intelligent AlphaGo. And so in principle, these systems never stop learning. It's just a matter of how many resources you want to sink into them. Now, with language models in RL, it's still early days. So I don't think that we've discovered the sort of maximally scalable blueprint, but there's a foothold. So to give you a sense, at least the way we see it, is that even when we look at DeepSeek R1, that is a more powerful algorithm than a normal RLHF algorithm, but it's still actually a fairly weak form of RL. It's what we call single step reinforcement learning, where you have, once you think for a long time and then you just generate a solution. And that's basically one step. But I think the natural evolution of these systems, especially ones that act on your computer, are systems that are going to be thinking and acting over multiple steps. So they think and act and so forth. And there's this outer loop of credit assignment across the steps. So I think we're just very early on in the story of how reinforcement learning plays out on top of language models. Before, it was similar in, let's say, when deep reinforcement learning started, DQN came out in 2013, and the arc to, AlphaGo 0 and Mu 0 didn't end until the late 2010s. So there was at least 5 years and a lot of progress is being made. I expect something similar to happen here, but on a compressed timeline. The amount of resources going into these things is just much larger. And I think we just move faster now. There's just a lot more infrastructure. And so I suspect that instead of 5 years, it'll probably be a matter of a couple of years before we see something like a super intelligent language model in some meaningful areas of knowledge work. So yeah, I think that reinforcement learning is not going to plateau.
Got it. I think I heard you say on another podcast that, you were about 3 years from AGI. And that I think maybe what you just said is reiterating that point. So, one of the things that I'm one shoe that I'm expecting to drop, i.e. somebody releasing a model of this type or paper, is that, doing RL where the model is taking actions on someone's computer or using their browser or something like this, that's got to be a very fruitful thing, because as you said, it thinks, it takes an action, it thinks it takes an action. Maybe it's trying to like buy something for you on the internet or something. And it's going to get feedback on each of those steps. So you could imagine that's like a super fruitful trajectory through the RL space. And yeah, I'm expecting someone to release a model that's just like extremely good at like doing things on, Amazon and eBay and a bunch of, commercial websites and things like that. So yeah, probably happens sooner rather than later.
It's possible. I think that this is kind of an interesting era that we're entering, because a lot of it depends on whether you can operationalize a good enough data distribution that's verifiable for these tasks. So I think that's kind of a big question when, for some browser-based things, there is just hard to collect good enough data for it. There's no repository of browser-based say tasks and rewards at large scale that's diverse. So when we see these reasoning models work, they work because there's diverse data pools for questions and answers for math and coding, like textbook coding. And so we know that these systems work when you have that kind of data structure, but in more practical scenarios where it's harder to access those data pools, I think you kind of have to get creative about how do you, if they don't exist in some, easy to access format, is there some strategy you can invoke that will basically get you the data that you need in a clever way? So I think a lot of it depends on basically how you operationalize data collection, which is it's definitely a hard thing to do. And one thing that is probably even more obscure than model training or things like that. When you read a DeepSeek paper, that is the one thing where they don't really tell you anything about, right?
Yes.
And I think the other thing that's really interesting is that reinforcement learning sort of, let's say, it couples to the environment that you train it in. So as soon as you have, I mean, right now we have these reasoning models, but as soon as you have environments with tools, let's say for code editing or browsers or, other ways to interact with a computer, and you run a reinforcement learning algorithm through that, it gets coupled to those tools. And so it actually loses generality, right? Because it might learn, unless you train it in some way if you train this very general reasoning sort of way, it might learn to kind of generalize to some new tools. But the system that's trained coupled to the environment is likely going to achieve much more depth-wise in that environment. So, right, if you are coupled to, let's say, a coding environment and a browser and some tools for doing science, and you have some way of verifying whether you're answering, say, scientific questions, the kinds that scientists care to answer correctly. So you solve the data distribution problem. Then you train a reinforcement learning algorithm against this environment, and it'll sort of really master the tools that you gave it in the environment, and but not generalize to, let's say, tools in other environments. So there's an interesting way in which RL methods are coupled to the environments that you train them in. And this is going back to what happened with reinforcement learning before language models, and that those systems were coupled to their environments. So AlphaStar was coupled to the StarCraft environment, AlphaGo coupled to the Go board. And I think now we'll see products where their reinforcement learning algorithms trained for some task set where the kind of neural network that's powering it is coupled to the environment that it was trained against. And an example of that, is, now I don't know if this is what's actually happening under the hood here, but when I look at a product like OpenAI's Deep Research that is powered by O3, it makes me think that most likely what's happening there is that the in tools for deep research, like the web browser and indices that they use for a language model to interact with, probably, O3 or whatever reasoning model was taken and then further trained as reinforcement learning against those tools to get something alive. Yeah. So I think that's kind of maybe the next, that's a limitation, but also maybe a benefit of the system.
So I myself and some other theoretical physicists I know have been experimenting with these reasoning models to just see, how useful are they really for our kind of research. And one of the things I discovered is it's quite good at finding stuff and summarizing it. But if I ask it to, maybe solve an actual research level problem or think about some research level thing, it'll often come back with what seems to be something more reflecting the consensus in the literature, which, could be wrong if it's a frontier level question I'm asking. And then the frustrating part is that if it were a grad student I was talking to at the whiteboard, I could course correct the grad student and the grad student would immediately update their neural connections based on what I tell them. And then they would then reason, correctly, subsequently incorporating that little nudge that I gave them, that update that I gave them. But what's frustrating about the models is I might discover some faulty reasoning or even contradictory reasoning in what it gives back to me. And I point it out to the model, but it can't really update on that. It just continues to give me the same line back. And so that sort of test time learning or test time memorization, maybe you saw this Titans paper. To me, that's super interesting. Is what's the right way for it to be able to actually update itself at test time? Have you thought at all about that kind of thing?
Yeah, I think it's an interesting problem. And in some sense, so these reasoning models kind of inherit the priors of the pre-trained model they were trained on. And again, we have to remember that the reinforcement learning methods they're trained with today are actually a pretty weak entry level for reinforcement learning. And so this to me is kind of, again, the statement that we're far from the Move 37 moment, or maybe not that far, because again, it's a matter of 2 years that's a matter of perspective. But when I say far, that's kind of what I mean. And it's very much, it goes back to the data distribution problem. Like how often did the model when it was being trained with RL or otherwise, did it see corrections and what the appropriate response is to that correction,
right,
and get that reinforced? And I think that there's a little bit of that. Like these models went from not knowing how to backtrack very well to backtracking. So now when you look at the R1's chain of thought, you'll see it oftentimes says, wait, maybe I should rethink this and go back. There are these pivot words, like wait, or oh wait, or hold on, which part of that was probably mixed explicitly in the data distribution that, you can run a reward verifier and see, especially if you have something that's per step, and see when it messes up and then inject an oh wait in there and then continue training on that. So I think a lot of that comes into how you sort of curate the data distribution that you train on. But fundamentally, I think that these systems have been trained with pretty weak RL. Mm-hmm. And so for that reason, they've learned some things that were not in the distribution of the pre-trained model initially, but in terms of generating net new knowledge, it's very hard. And I actually had a very similar experience to you. I was wondering if it could reproduce my PhD thesis, was basically what I was wondering. And my PhD thesis, even though it was a lot of working on it, but I can, actually summarize the thing that was done like fairly quickly. Mm-hmm. And if you kind of, if you pose the question the right way, it's a somewhat likely derivation, but there are only like a couple of key parts that are really tricky. And effectively my PhD was on studying the various characteristics of the fractal quantum Hall effect and doing perturbation theory kind of approximation of the electron density for various fractional Hall states. And basically, when you expand this thing, the first two moments are really easy to find. Like the first moment is basically undergrad physics. Second moment is a graduate course in statistical mechanics. And the third moment, which has this very interesting physical constant on it, it's kind of a geometric characteristic of a fractal quantum Hall state, was something that I had discovered during my PhD. And that one is non-trivial. Like that one, you need a PhD on to solve it. And no matter how I prompted it just couldn't get it. Right? It only got the first two, like things that are in textbooks, basically. Yes. And it was not able to generate that net new knowledge.
Yeah, I think so. I think that's the current feeling of people, that it is still useful. Like if I don't know an area and I'm just trying to get a summary of what's already known in the literature, it can succinctly, deliver that. But pushing forward is just extremely hard for anything that's really not present in a strong way in the existing literature.
Yeah, exactly. Let's come back to 2 years from now and see what happens. I think especially in physics and theoretical mathematics, that might see the changes there faster than in other fields.
Yep. So I know you have a hard stop, and so we're about 5 minutes out until your next meeting. And so let me just end with one last question. So what's special about your perspective on AI coming from a background in theoretical physics? Is there anything unique about the perspective that you bring? I think I asked John Schulman about this in another interview, but I'm curious what you think.
It's a good question. Well, I think physics teaches you, first, physics is really hard. So when you get into AI, AI is a lot easier than physics. At least that was my perspective. Picking it up was a lot faster. So you're kind of unfazed by the mathematics. And the thing that you have to learn, you have to learn how to code, and that's challenging, and becoming a really good engineer is very hard. But, once you go through the, physics grinder, it's, I think the willpower you have to kind of learn things is sufficient. So it's all possible. I think something that's special is that this thing, it might be obvious to physicists, of trying to understand things from some kind of simple set of first principles. Yep. And deriving things from there and looking for simple solutions is not that obvious, or maybe even common in AI. Like a common actual way to write an AI paper is to, or was, and I'm sure it's still somewhat true in academia now, but it was take an architecture, make it more complex, like take your algorithm, make it more complex, like add complexity to get some performance gains, and then, write a paper about that. And I think that that's actually the probably most common way of operating as a researcher in AI, is that you take something that exists and you push it forward by making it more complex and getting some performance gain. But that's very short-lived. I'm not even sure if I've read any impactful papers that's the template for writing a paper for a conference, but I don't know if any impactful papers actually had that template. And this perspective of coming in and actually trying to simplify things and do even the simplest thing, and also coming in with a blank slate and having kind of no preconceptions is very helpful. An example of this was I came into reinforcement learning, had basically zero preconceptions around what works, what doesn't. And this was when people were studying reinforcement learning pixels, when you're training from, for robots or video games. And there are all these questions of RL is great, but it's not data efficient. Sometimes it doesn't work on these pixel-based environments. And one of the papers, my first papers, did a very simple thing. It's just kind of tried, well, what if we just basically jitter the images, just randomly crop them, because maybe it's just kind of, these systems are just always seeing the same perspective. And so they're kind of memorizing it. And this was, I took I took a good implementation by a different colleague of the reinforcement learning algorithm called Stop Actor Critic, implemented this random cropping, basically this jittering of the camera. And lo and behold, that simple thing outperformed at the time, basically all the state of the art algorithms that had this additional level of complexity. So I'm not saying that was a particularly beautiful idea or not impactful, but it was just surprising to me that no one had tried this very carefully before. And so I think that's an interesting perspective. This brain is sort of trying to simplify the problem as much as possible into its core principles. And in some cases, I would say some of the most impactful work that's come out of physicists coming into AI has been the work on scaling laws. This was taking a perspective of scaling laws that occur at critical temperatures and, in theoretical physics or around critical phase transitions. And noticing that, there are these, scaling laws that have, universal, physical characteristics attached to them. And, that perspective that something like that might be happening when you're training these deep learning models, was not obvious to people at the time. And so the folks who led that work at OpenAI and scaling laws were not even former physicists, or they were kind of, I think, either very recent former physicists or current physicists at the time.
I think Jared still has a job at Hopkins. I'm not sure, but he could still, he's maybe technically still a physicist. But hey, I don't want to make you late for your next meeting. So really enjoyed this conversation. Maybe have you back in 2 years when we have AGI in our pocket. And thanks so much.
Yeah, of course. Thanks for having me, Stephen.